11 billion years ago, two galaxies slammed into each other. The collision compressed the cloud of molecules so violently they started lasing, a natural radial laser firing out into space. The beam has been traveling ever since. Last month, a telescope in South Africa caught it. That's your cold open. Let's get into it. You're listening to Stardrift FM. Tonight, the most distant cosmic laser ever detected. A cold spot in Jupiter's northern lights that no model can explain. A planet 10 light-years away that might be the best place we've ever had to look for life. Mars absorbing 200 days of radiation in 64 hours. A SpaceX rocket poisoning the upper atmosphere, and the first direct proof of it. And Europe is launching its own GPS constellation 2 weeks from now. 6 stories. Let's go. Story 1. The MeerKAT telescope sits in the Karoo Desert in South Africa. 64 dishes spread over 8 kilometers of red dirt, pointing at the sky. Earlier this year, it picked up something that had never been seen before at that distance. A hydroxyl megamaser, which sounds complicated, but the physics is actually straightforward. When two galaxies collide, and we're talking full galaxy collisions, billions of stars crashing through each other over millions of years, the gas clouds between them compress. That compression pumps molecules to excited states. And when those molecules relax, they emit radio photons in lockstep, coherently, the same way a laser works but at radio frequencies, a natural maser. Megamasers are 10 million to a billion times brighter than ordinary galactic masers. We've known about them since the 70s, but they've always been found relatively nearby in astronomical terms. The record, set in 2022, was 5 billion light-years. This new one is at a redshift of z equals 1.027. That puts it at 11 billion light-years. We're seeing it as it existed when the universe was less than 4.7 billion years old, less than half its current age. There's a bonus: a foreground galaxy happened to line up perfectly between us and the source, acting as a gravitational lens. It magnified the signal 10 times. Without that, MeerKAT probably couldn't have detected it at all. Lead author Thado Manamila, a postdoc at the University of Pretoria, said, "This is just the beginning. We don't want to find just one system. We want to find hundreds to thousands." MeerKAT is a precursor to the square kilometer Aurora, which will be 50 times more sensitive. When SKA comes online, this kind of detection becomes routine. Story 2. Jupiter has the most powerful aurora in the solar system. Hundreds of times brighter than Earth's northern lights, and it never stops. The main driver isn't the solar wind, it's Io. Io is the most volcanically active body in the solar system. Its eruptions constantly inject sulfur into a plasma torus that rings Jupiter along Io's orbital path. As Jupiter's magnetic field, which rotates every 10 hours, sweeps past Io, the speed mismatch generates an electric current of about 1 million amps. That current flows along Jupiter's field lines down into the atmosphere, and where it hits, you get a bright auroral footprint, a spot on Jupiter's surface permanently anchored to Io's position in the sky. JWST observed Jupiter's northern aurora for 22 continuous hours in September 2023. It was the first time anyone had used a spectrograph to actually measure the physical properties of those footprints, not just how bright they are. Temperature, ion density, the real numbers. And in one of 5 observation snapshots, something appeared. A cold spot inside Io's auroral footprint. Temperatures of 538 Kelvin, 265 Celsius. Compared to the surrounding aurora at 766 Kelvin, nearly 500 Celsius. 228 degrees colder, and simultaneously 3 times denser with ions than the main aurora. Cold and dense together is counterintuitive. More particles means more collisions, which means more heat. Something is actively cooling that region, or redistributing energy in a way no current model predicts. It appeared once, in one of 5 snapshots. Lead author Katie Knowles, a PhD researcher at Northumbria University, put it plainly: We only saw this phenomenon in one of our 5 snapshots, which leaves us with questions. How often does this occur? Follow-up observations were scheduled with NASA's Infrared Telescope facility in January 2026, 32 hours of continuous monitoring. We don't have those results yet. Story 3. 10.7 light-years from Earth, there's a star called JWST, a red dwarf, the most common type of star in the galaxy. You've probably never heard of it, but astronomers have been watching it for a while. And this week, a team from Bulletin and St. Andrews published the confirmation of something significant. 4 planets, one of them in the habitable zone. The habitable zone planet, JWST, has a minimum mass of 6.1 Earth masses and orbits every 50 days. At its distance from the star, it receives enough starlight that liquid water on its surface isn't ruled out. That makes it the second closest known habitable zone planet to Earth, after Proxima Centauri b, which is 4 light-years away. But here's what makes JWST interesting beyond just the distance. Most red dwarfs are violent. They flare constantly. X-ray and UV bursts that could strip a planet's atmosphere in geological timescales. JWST is unusually quiet. Slow rotation, 38 days. Nearly constant brightness. Its planets aren't being bombarded every few hours. It's also the brightest M dwarf in the sky. That matters enormously for future observations. Brighter star means higher signal points when you're trying to detect an atmosphere. The team also confirmed a near-Earth mass planet at just 1.46 Earth masses detected at sub-meter per second radial velocity. That's a very small signal for a very small planet. The Habitable Worlds Observatory. NASA's next large space telescope has JWST on its prime target list. If it launches this decade, we'll have a real shot at looking for oxygen, water vapor, or methane in the atmosphere of that habitable zone planet. Not guaranteed, but genuinely in scope. Story 4. In May 2024, the Sun had one of its biggest outbursts in 20 years. Sunspot region AR3664 fired an X-12 class flare, part of the same storm that produced auroras visible from Mexico. On Earth, the magnetic field absorbed most of it. On Mars, there's no magnetic field, and 2 ESA spacecraft were watching. Mars Express and ExoMars Trace Gas Orbiter have been using a technique called orbiter-to-orbiter radio occultation for about 5 years. One spacecraft transmits a radio signal to the other as it disappears behind the Martian limb. The signal bends through the atmosphere, and the bending pattern reveals the density of charged particles at different altitudes. It's how they caught the storm. The numbers published this month in Nature Communications, electron counts jumped 45% at 110 kilometers altitude. At 130 kilometers, they jumped 278%. Both ionospheric layers were pushed 6.5 kilometers upward. NASA's MAVEN independently confirmed it, calling it the largest solar energetic particle event in its decade of operations. TGO's radiation dosimeter absorbed the equivalent of 200 normal days of radiation in 64 hours. Both spacecraft suffered computer errors, bit flips from energetic particles. They survived because they're built for it. A human crew would not have been. The deeper connection is this. Mars lost its magnetic field 3.7 to 4.2 billion years ago. Without it, there's nothing to deflect the solar wind. Events like this one, multiplied across billions of years in a much more active early sun, explain why Mars went from warm and wet to the frozen desert it is today. Lead author Jacob Parrott from ESA's Research Center in the Netherlands. The impact was remarkable. Mars's upper atmosphere was flooded by electrons. It was the biggest response to a solar storm we've ever seen at Mars. The timing was, in his words, extremely lucky. The radio occultation window at Mars opens twice a week. Story 5. On February 1st, 2025, a Falcon 9 upper stage launched from Vandenberg carrying Starlink satellites. The deorbit burn was supposed to happen about 90 minutes later. It didn't. A liquid oxygen leak had disabled the engine. The stage spent the next 18 days in uncontrolled orbit. On February 19th, it came down, a fireball tracked across Ireland, the UK, the Netherlands, Germany, and into Poland, where debris was recovered near Poznan. Standard re-entry happens regularly with upper stages. What happened next was not standard. 20 hours after re-entry, a LiDAR system at the Leibniz Institute of Atmospheric Physics in northern Germany made a measurement it had never made before. At 96 kilometers altitude, the mesosphere, the part of the atmosphere too high for aircraft and too low for satellites, a spike in lithium atoms. The baseline was 3 atoms per cubic centimeter. The measurement showed 31. To confirm the source, the team ran 8,000 backward wind trajectory simulations from the LiDAR station. The ensemble converged on the Falcon 9 re-entry path over Ireland. The lithium had come from the rocket's aluminium-lithium alloy hull and its lithium-ion batteries, about 30 kilograms total. It had drifted 1,600 kilometers eastward in 20 hours. This is the first time a specific piece of hardware, named mission, named manufacturer, has been directly linked by measurement to atmospheric contamination at altitude. Previous research on this was modeling. This is data. The context: at peak Starlink deployment, an estimated 29 tons of satellite material enters the atmosphere per day. Aluminium oxide particles from satellite reentries act as catalysts for ozone destruction. Unlike CFCs, which get consumed, a single particle can destroy thousands of ozone molecules without being used up. The effects of today's reentries won't reach the ozone layer for another 20 to 30 years. Story 6. 2 weeks from now, on March 24th, a Rocket Lab Electron will lift off from the MeerKAT Peninsula in New Zealand carrying 2 small satellites. IOD-1, a 12-unit CubeSat built by GMV and OHB. IOD-2, a 16-unit CubeSat from Thales Alenia Space. Together, they are the first launch of ESA's Celeste constellation. Celeste is ESA's attempt to build a low Earth orbit navigation layer to sit alongside Galileo. Galileo operates at 23,000 kilometers altitude, medium Earth orbit. Celeste flies at 500 to 560 kilometers, 40 times closer to Earth. At that altitude, the signal reaching the ground is roughly 1,000 times stronger. The timing isn't coincidental. European airspace has been experiencing significant GPS jamming and spoofing since the conflict in Ukraine began. Baltic states, Finland, Poland, the Eastern Mediterranean documented disruptions affecting civilian aviation and shipping. Galileo's L-band signals are vulnerable to the same interference. Celeste adds C-band and UHF bands to the mix, which are substantially harder to jam, and it tests 5G satellite waveforms with built-in spread spectrum resistance. There are already 5 billion smartphones on Earth that receive Galileo signals. Celeste would eventually add 11 demonstration satellites in low Earth orbit, the first 2 on this flight, with the rest following from 2027. Rocket Lab Electron has completed 83 launches, deployed 249 satellites. It's a proven vehicle. This mission is a demonstration, not a full operational constellation, but it's the first concrete hardware in orbit for a European sovereign low Earth orbit navigation system. ESA project manager Roberto Prieto Cerdeira described it as opening a platform to work with end-user communities in real-world conditions. Launch window, March 24th. Watch live on ESA's channels. 6 stories this week. A laser from 11 billion years ago. A cold spot in Jupiter's Aurora that shouldn't be there. A quiet red dwarf 10 light-years away with a planet in the right place. Mars showing us exactly what happens when a planet loses its magnetic field. A SpaceX rocket leaving a traceable lithium trail in the mesosphere. And Europe's first low Earth orbit navigation satellites launching in 2 weeks. Stardrift FM. See you next week.